The deepest parts of our oceans are the quietest libraries on Earth. For millions of years, a gentle rain of dust, ash, and microscopic life has settled on the seafloor, building up layer by layer, like pages in a book. These sediment cores hold a detailed diary of our planet's past. Every volcano that erupted, every ice age that came and went, every shift in ocean currents. But how do we read this watery history book? And what urgent story is it telling us about our future? Welcome to Boson Buzz. I'm Monty Molecule, and today we're diving into the mud to listen to the planet's long memory. We're meeting the deep-sea librarians, the ocean's memory. Our story begins with a mystery from the past. Scientists want to understand a sudden ancient cold snap called the Younger Dryas, a period about 12,000 years ago when the world, which was warming after an ice age, suddenly plunged back into freezing conditions for over 1,000 years. What caused it? Land records from glaciers and lakes are patchy. To solve this, we need a continuous global record. We need to go to the bottom of the sea. The old way of studying ocean history is powerful, but limited. Scientists take core samples, long tubes of mud from the seafloor. They analyze them layer by layer, which is incredibly slow, like reading a million-page book one letter at a time. It can take years to study just one core from one location. To see the big picture of global climate, we need to read many books from many libraries, and we need to read them much, much faster. Enter the new deep-sea librarians. Modern research vessels are now equipped with a revolutionary tool, the automated core scanner. This isn't just a tube. It's a laboratory that reads the mud the moment it comes on deck. The long cylindrical core is placed on a conveyor that moves it past a battery of sensors. First, an X-ray scanner looks inside the core without opening it. It reveals density changes, the difference between a layer of thick clay from a quiet period and a layer of coarse sand from a powerful underwater landslide. It can even spot tiny ash particles from a volcanic eruption thousands of miles away, each layer a timestamp. Next, a hyperspectral scanner passes over the core's surface. It doesn't just see color, it detects the chemical fingerprint of every millimeter. It can measure the amount of calcium, telling us how much microscopic plankton life there was. It can detect specific molecules that are only produced when water is very cold, acting as a tiny thermometer frozen in time. Finally, the core passes by a magnetic sensor. As sediment settles, tiny magnetic minerals in the particles align with the Earth's magnetic field, which has flipped north to south many times in history. These flips are global time markers. By detecting these magnetic reversals in the mud, scientists can match the ocean core's timeline with records from ice cores and rocks on land, creating a perfectly synchronized planetary clock. All this data streams into the ship's computers in real time. Powerful software assembles it into a vivid timeline, a climate movie made from mud. Scientists can watch as, layer by layer, the chemistry shifts, showing the ocean getting colder or more acidic. They can see sudden spikes of ash from megavolcanoes and the slow, steady rise in certain gases that correspond to warming periods in Earth's deep past. Now, let's return to the mystery of the Younger Dryas. By comparing ultra-detailed scans from dozens of cores across the Atlantic, a clear story emerged. Just before the cold snap, there was a massive influx of freshwater detected in the North Atlantic layers. The hypothesis? A giant lake of meltwater from the retreating ice sheets suddenly drained into the ocean. This freshwater cap shut down a crucial ocean current, the Atlantic conveyor belt, that brings warm water north. Without that heat pump, Europe and North America froze. The ocean's memory didn't just record the cold, it recorded its cause. But this isn't just about ancient history. The same layers that hold the secret of the Younger Dryas hold urgent warnings for our future. By reading the chemical clues from past warm periods in Earth's history, scientists can see how the ocean behaved. They can see how acidic it became when carbon dioxide levels were high, and how that affected shell-building creatures. They can measure how fast sea levels rose when ice sheets collapsed. These are not computer models of the future. These are physical receipts from the past, showing us what happens when the planet gets hot. The power of the ocean's memory is now being scaled up. Robotic seafloor drones are being designed to stay underwater for months, collecting and scanning cores from remote, icy seas we can barely reach by ship. International teams are sharing their core scan data, building a single, open digital library of Earth's climate history. This allows a scientist anywhere to pull up the record from the Southern Ocean or the tropical Pacific and compare it with their own, building a truly global understanding in days, not decades. This deep-time perspective is our most powerful tool for forecasting. By understanding the precise conditions that triggered past tipping points, like the collapse of ice sheets or the shutdown of currents, we can better monitor our own world for similar warning signs. The mud isn't just about the past, it's a mirror held up to our possible futures. It gives us a profound perspective, doesn't it? We are not the first to change the climate, but we are the first to be able to read the instruction manual written in the mud, to see the consequences of our actions written in advance. It's the promise of learning from the planet's own long history, of using the deep ocean's quiet records to navigate the storms of our future. If this idea of reading Earth's diary in the deep sea resonates with you, please like and subscribe to Boson Buzz. Until next time, have a safe and curious week.